All right, welcome to our sixth and final lesson for Unit 8.5, Stoichiometry. Today's lesson is variations on the stoichiometry problems that you're going to see. Most of the stoichiometry that we've been working with has been gram-to-gram stoichiometry, where you are given a number in grams for one substance, and you are asked to convert to grams of a different substance. And so that became a three-step problem, three conversion fractions, where the first fraction converted to grams to moles using molar mass. And then the second fraction was moles to moles using the coefficients from the balanced equation. And then the third fraction was going from moles to grams of the substance you're trying to solve for. And you had to use the molar mass of that substance. Okay, and so just a quick refresher. You have 64 grams of oxygen gas. How many grams of hydrogen gas will be needed? So you are given a quantity of oxygen and being asked to find a quantity of hydrogen. And so we can see here that 64.0 grams of O2, if we set that up, grams of O2 in the denominator, 1 mole of O2 in the numerator. We know the molar mass of oxygen is 16 times 2 is 32. So that's our first fraction, the molar mass of the original substance. The second fraction uses the coefficients from the balanced equation, which are 2 to 1 to 2. And so canceling out moles of O2, we're trying to find for hydrogen gas, so we're going to go to moles of H2. And from the balanced equation, we see that it is 2 moles of H2 to 1 mole of oxygen. Last fraction, we're going to go from moles of H2 to grams of H2, where 1 mole of hydrogen weighs 2.02 grams, right? And so we've done a number of these problems, so you must be getting pretty good at manipulating the units. 64 divided by 32 times 2 times 2.02 gives us 8.08 grams of hydrogen gas, right? So that's been the standard stoichiometry problem. We're going to change it up a little bit. That's why this lesson is called Variations. And one way that this can get varied is instead of needing all three of those fractions, you might only need one or two of those three steps. So you're going to have to pay attention to what quantity you are given and what unit that is in, and what unit you are trying to determine for the other substance. So in this example, I'm going to give you grams of the first substance, and I'm going to ask you to find moles of the second substance. Okay, we're still going to be basing it on the equation 2 hydrogens plus 1 oxygen turning into 2 H2O. We're going to use that for simplicity's sake to help us figure out these problems. All right. So let's say I give you that same amount of oxygen gas to start with, but now I'm asking you to find moles of hydrogen. The previous problem I was asking you to find grams of hydrogen. So this problem is going to start the same way. Grams of O2 needs to cancel. We're going to convert that using molar mass. 1 mole of O2 is 32 grams. You know, if I stop the problem here, all I've done is I've converted grams of oxygen into moles of oxygen. Keeping in mind, we're trying to find moles, but we're trying to find moles of hydrogen. So here's where we're going to need the second fraction, where we convert moles of oxygen into moles of hydrogen. So from the balanced equation, we've got 2 moles of hydrogen, 1 mole of oxygen. If I stop here and consider moles of O2 canceling, if I stop the problem here, my answer will be in moles of hydrogen, which is what we are trying to solve for. So here's a problem where it's almost a gram-gram problem. We just didn't need to do the final molar mass of hydrogen problem, right? So, if we calculate this, 64 divided by 32 times 2, we're going to get 4 moles of hydrogen. Okay. Using that same equation, okay, in this case, let's say the camera's just about falling off. Sorry about that. Sorry if that makes you queasy. If I give you moles of the first substance and ask you to find grams of the second substance, let's see how that changes the problem. So I'm given 2 moles of oxygen gas. How many grams of hydrogen gas will be needed? So I'm going to start with that given quantity, 2.00 moles of O2. And when you are starting with moles in a stoichiometry problem, right, previously we started in grams, so the first fraction we needed was a molar mass. But when you're starting in moles, you don't need this first molar mass. You're going right to the mole ratio fraction. So moles of O2 on the denominator and moles of H2 in the numerator. Moles of one substance to moles of another is the coefficients from the balanced equation, right? And so 2 moles of hydrogen to 1 mole of oxygen. If I were to stop here, moles of O2 will cancel, leaving me with moles of hydrogen. But this problem is asking me to find grams of hydrogen. So I need one more fraction where I cancel moles and I convert it to grams of hydrogen. This is a molar mass, moles to grams. So 1 mole of hydrogen is 2.02 grams. We can recognize that moles of H2 cancel. It leaves us with a unit of grams of H2, which is what we're trying to solve for. So the math becomes 2 times 2 times 2.02, and we are going to get to 3 significant figures, 8.08 grams of H2. Okay, so this comes down to paying attention to what's being given and what unit it's in, and figuring out what you are trying to get to and what units it's in. Okay. Well, we can continue to layer this on because we can make even more variations happen. You may also see problems that involve particles and or volumes of a gas. In this case, it may be helpful to bring back the mole map, but we're going to add to it, right? You might notice in these problems, we always have 2 substances from a chemical reaction. You're given a quantity of one substance, and you're being asked to convert it to a quantity of a different substance. So each mole map is for each substance. So let's say this mole map, we'll think about it for the first substance, meaning the given substance. And the other mole map is for the second substance, which is the thing you are trying to solve for. Now, the only way these 2 mole maps connect is from the moles. Okay? The only way you can go from a mole map of one substance to a mole map of another is through a mole ratio, right? That mole ratio. And that comes from the coefficients of the balanced equation. So let's take a look and see how this works. All right. So in this first example on this side of the handout, I'm going to give you grams of the first substance. So let's say you're starting with grams of the first substance, and I'm asking you to find particles of the second substance. So I'm asking you to go to the particles over here. So here's how that's going to work. You're going to need 3 fractions. The first fraction is going to be, you're going to go from mass to moles using molar mass. So your first fraction is going to be molar mass of substance number 1. The next fraction is going to be moles to moles, where you're going to use the coefficients from the balanced equation. And then the third fraction is going from moles of the second substance to particles of the second substance using the fraction 1 mole is equal to 6.02 times 10 to the 23. So let's try this. Let's see if we can't put all of this together, and I'll try to keep the map in the view of the camera here. So we are given a quantity of oxygen. We are finding out how many molecules of water. So our first substance is oxygen, our second substance is water. So So we're starting with the given quantity of 12.8 grams of oxygen. And remember, in our map, to go from mass of the first substance to particles of the second substance, I have to first convert to moles of the original substance. And then, so let's start with that before I review the whole thing. So you're starting with mass of the first substance going to moles of the first substance, using 1 mole is equal to the molar mass of that first substance. So grams of O2 in the denominator, moles of O2 in the numerator. So 1 mole is equal to the molar mass of O2. Since each oxygen is 16, 2 of them will be 32.0 grams. Okay, the next fraction will be moles of the first substance converting to moles of the new substance from the coefficients of the balanced equation. We just have to remember that we need to cancel out moles of O2, and we're going to convert that to moles of the second substance, which is water. From the balanced equation, moles of O2 is 1, and moles of water is 2. Okay. So I've gone, my first fraction to use the molar mass of oxygen. My second fraction used the coefficients from the balanced equation. My third fraction, I'm going to need to cancel out moles of H2, right? Because now I'm going to particles. So my fraction here is going to use 1 mole is equal to 6.02 times 10 to the 23 molecules of water. Okay, so let's confirm that units are canceling appropriately. Grams of O2, cancel. Moles of O2, cancel. Moles of water, cancel. The only unit that does not cancel is molecules of water. So let's go ahead and do this in the calculator. We've got 12.8 divided by 32 times 2 times 6.02 times 10 to the 23rd. So we get an answer of, to 3 significant figures, 4.82 times 10 to the 23rd molecules of O2. All right, let's try one more together. I'm going to give you liters of the first substance, and I'm asking you to find moles of the second substance. Okay, so let's just take a look at the game plan. You're going to start with liters of the first substance. So going up to my map, starting with liters of the first substance, trying to get to moles of the second substance. So this one's only going to require 2 fractions. Can you see them? The first is going from liters to moles, using 1 mole is 22.4 liters. The second fraction is going to be using the coefficients of the balanced equation to convert from moles of the first substance to moles of the second substance. And then I stop. I only will need two fractions in this problem. So let's try to put that together. We're being asked to find moles of hydrogen. How many moles of hydrogen will be needed in order to completely burn with 78.4 liters of oxygen? So I'm going to start with my given quantity, 78.4 liters of O2. And again, I'm still working with the same chemical equation. Still working with this same equation. So first thing I need to do is cancel out liters of O2. And I'm going to convert that to moles of O2. And remember, this is where 1 mole of O2 is 22.4 liters. Right? So if I go back to my map, I started in liters, and I'm converting it to moles of that same substance. I'm trying to get to moles of the second substance. So I just need one more fraction that uses the coefficients from the balanced equation. Remember, you always want to cancel out the unit that is in the previous fraction in the numerator, so moles of O2 in the denominator. And then moles of what you're trying to convert to, in this case hydrogen, goes in the numerator. And then from the balanced equation, the coefficient in front of the hydrogen is a 2, and the coefficient in front of the oxygen is a 1. So let's take a look. Liters of O2 will cancel. Moles of O2 will cancel. And that leaves me with moles of hydrogen, which is what I was trying to solve for. So now that I'm confident I've set up my problem, I can go ahead to my calculator. 78.4 divided by 22.4 times 2. And my answer here is 7 in my calculator, but I want to maintain the 3 sig figs, 7.00 moles of H2. So there you have it. You've seen this is sort of putting a lot of things together from this unit, and I hope that the mole map helps you visualize what your problem solving strategy is going to be. Go ahead and try the problem set on your own, and as always, ask questions and check your answers, and let me know how I can help you. All right, thanks so much. We'll see you back in the classroom.